guess we can start. Hello everyone. So this is the last session of this conference. We've left you the best for last. It's my pleasure to introduce Professor Adji Bousso Dieng, who is an assistant professor of computer science at Princeton University, where she leads Vertex on research at the intersection of both AI and the natural sciences. She's affiliated with the Department of Chemical and Biological Engineering, the Princeton Materials Institute, the Princeton Quantitative and Computational Biology, and the High Meadows Environmental Institute. And she's also a research scientist at Google AI and the founder and president of the nonprofit, The Africa I Know. She's had so far a brilliant career. Since her PhD at Columbia, where she was a Google PhD fellow, she has received many recognitions. For example, she was recognized as an AI 2015 Early Career Fellow by Schmidt Features and an outstanding recent alumni by the Columbia Graduate School of Arts. And today we're hoping to learn from her multidisciplinary experience as she shares with us her thoughts and insights on how AI is being used in the natural sciences, the pitfalls that need to be avoided for AI to make positive impact in those domains, and the role that accounting for diversity in AI can play in that. So the floor is yours.
Thank you, Dr. Ava, for this nice introduction. Let me share my screen. This is fine. Okay, great. I'll go ahead and start. So today my talk is titled The Scientists' Work in the Age of AI. Most of what I'll talk about is around chemistry and material science, but I think it applies to many other sciences, in many other natural sciences. So typically the discovery loop in material science for an experimentalist is, you specify a set of desired properties that you want for a material. Say you want a material that's very conductive. That's your requirement. Now you want to go ahead and see how you can design a material, make a material that exactly satisfies those properties. For example, being very conductive. First, you hypothesize what the material should be made of, and that requires a lot of domain knowledge. These are people who are trained in material science and in chemistry, and they have strong knowledge and intuition around, what should compose a material when you have certain target properties. And then once they hypothesize what the material should be made of, then they run experiments in the lab to try to synthesize that material. And then once they synthesize, you measure properties of the material you just made, and you check whether the material you made satisfy those properties. Most of the time, it does not, because, things are never perfect. So you have to fine tune, go back through this loop of trial and error until you get the desired material. And this loop requires a lot of domain knowledge and intuition, and it takes a lot of time. And so people have leveraged AI to make this loop faster. So it's AI for discovery in material science. The goal is to make the entire discovery process very fast so that we can make discoveries at a fast pace. So in this first part of the discovery, where you have to hypothesize what the material is made of, there are different ways to do it using AI. You can do generative modeling or active search in general, or sampling. For generative modeling, you use a database of existing materials, and then you build a generative model on top of that. You train a generative model on top of that data, and then you use that generative model now to get new candidates that can satisfy a certain chemistry or symmetry or property that you want. So this is inverse design with generative modeling, and it's an active area of research. You can also do search and experimental design, for example, Bayesian optimization, where you start with some known labeled set, so materials and properties, and you train a neural network, for example, a model that can predict those properties using materials, and you use that function to design an acquisition function, typically based on a Gaussian process. So the mean and the sigma of a Gaussian process, and use that to define an acquisition function that will allow you to select data, that new data that you will add to your labeled data, and you go through that loop until you build you find the material that you're looking for. Sampling is another alternative where you are actually, the energy function from which you want to get the material from, the energy function, and you want to be able to sample from that energy function in an efficient way. So people have developed methods that make sampling better for these things. Once you have these candidates from a generative model or a search algorithm or a sampling algorithm, what you want to do is be able to take that candidate and predict properties. That's the third part of the experimental loop. And so what we've been doing in ML AI is three ways of going about that. You can use the material the candidate material. For example, if it's NaCl, you take that candidate material, you pass it through a graph neural network, and you let that graph neural network predict the property. Say your property is bend gap or volume of the unit cell, or whether the gap is direct or not. So these are different types of properties. You can use this structure of the material, pass it through a graph neural network, and try to predict the property. Another way people have been doing it, our lab has innovated in this space, is to actually, instead of using the structure directly, you use a description of the structure, and you use an LLM to trained on this to predict the properties. And we've seen that that does better in the work we put out very recently. Those are two ways of going about predicting properties. The third way is to directly try to solve the Schrodinger equation using neural networks. And this is FermiNet, for example, is one neural network from DeepMind that approach the problem like that, where you train a neural network to take the structure, the candidate, and give you the wave function, which is a solution to the Schrodinger equation. And once you have access to the wave function, you can predict any property, basically. So these are ways of going about that. And now the third part, once you have, predicted the property, you want to be able to synthesize the material. It's not just that you get something from, let's say you get an output from a generative model and the property is right. You want to go now and make that material in the lab. So AI is also helping in that step of the discovery process. So people have been using large language models that are trained on scientific literature, right? Because in scientific papers, they report their synthesis protocol. When they discover a new structure, a new molecule, a new material, they will have part of the paper describing exactly how they synthesized it. And so if you get a lot of those papers, you can train an LLM on top of it so that you can do prompting in order to ask your model, your LLM, how to synthesize a given material that you want or a given molecule. An alternative way for synthesis now is to actually not just use an LLM, which is indirect, because once the LLM gives you a synthesis recipe, you will still have to go and make it in the lab. And that synthesis recipe may be wrong as well. So this is just a way to, help with the synthesis so that you don't waste resources trying something that may not work. But there's a radical way of going about synthesis and completely getting rid of the experimentalist itself. So there's this fear that jobs will be lost in the sciences. So experimentalists are the ones who are most at risk when it comes to advances in AI for synthesis, because people are now working on developing self-driving labs where you can actually do the entire synthesis using robots. And there are people at Berkeley National Lab recently who showed that some promise in actually a full self-driving lab being able to synthesize materials. And I think we will get to a point where that process of experimentation, synthesis will be fully automated. So I think when you talk about future of work, when it comes to the experimental scientists, I think there's a risk there. But I always believe that jobs that are taken by automation can be rewired to new jobs that are enabled by that technology. So yeah, I think that's just something to keep in mind. And so my belief is that the future of the scientists' work in the age of AI will have to involve AI, because it can accelerate the entire discovery process. The problem is that there are roadblocks to AI enabling and accelerating scientific discovery. And I'll list here some of those roadblocks. Those roadblocks is data. Most of interesting scientific data are closed source, because getting that data itself is scientific output. That is what actually they publish. For example, synthesis and things like that. So data typically is the currency in the sciences, and so there is incentive in not sharing data, so that you can publish the data and you can publish paper on it and make your career out of that data that you made in your lab. So there's that problem of data being closed source and scarce. Also, there's no automated curation for large databases. If you have very large databases, in order to build AI models, you would want to query those databases in an efficient way. There's right now no automated way of doing that data curation without having to do expensive searches of databases. There's a lack of benchmarking. We have a lot of benchmarks in AI, but in the sciences, there are few of those, not many. The ones that actually are doing a good job are Materials Project, which is a good benchmark. There's also Open Catalyst, which is another good benchmark, but there are very few of those. So there's a lack of benchmark in this space. There are reproducibility issues that, in AI, we have a lot of that problem. In AI applied to sciences, that becomes even a bigger problem because of closed sourceness. So reproducibility issues is another roadblock to AI in science. Bad evaluation metrics. Our AI methods, we are able to do human evaluations because we're dealing with text and images and computer vision in natural language, where we have made a lot of progress. The things you're seeing right now, like ChatGPT, all of those are, text LLMs, and those big advances we've made in AI, they are in the domain of computer vision and natural language. And I think it's because we can do evaluation without worrying too much about whether these metrics are good or not. And we can rely on human evaluation. So we send these outputs from these generative models, so send images and text to mechanical turkers, and they can tell us whether they look good or not. But for the sciences, you cannot really outsource evaluation because it requires domain knowledge that not everybody has. It's not something that you can outsource to everyone. So there's that problem in terms of evaluation, and the metrics we use are also not optimal. And I'll show an example of a bad metric used in AI for science. Another problem is that our methods are data hungry. For our AI methods to perform well, they tend to require a lot of data. And so that can be a problem where in many areas in the sciences, there's only a few data points available. Data are black box, and the scientist typically cares a lot about interpretability. Being able to interpret how something was made can allow you to discover the mechanisms of that of formation for that structure and things like that. And also there are only few methods for quantifying uncertainty in AI for science, and we need more of that. We need good generative models and better sampling and search algorithms in general. And we saw that those are the ones that are underlying the entire discovery loop for AI for material science, at least. And for these generative models, sampling and search algorithms, we would want them to have high fidelity validity, meaning that their outputs need to be valid. They shouldn't collapse, meaning they shouldn't only get stuck in certain area of your space. You shouldn't just be outputting the same type of material. You want to be outputting a diverse set of materials, for example. We don't want generative models, for example, that memorize training data, because there's no discovery in that. That's just a database, and we don't want that. We don't want duplication. We want to have unique set of structures to look at. And we want data efficiency. We want to be able to curate good, reasonably sized data that we can use to fit models to. And so I think all of this ties to diversity. So for AI, I think for AI to effectively enable discovery, we ought to rethink diversity. This is why my lab has started with the study of diversity, and we've seen in some of in the works we've done that it can help in a lot of areas of science, and I'll discuss a few of those right now. First of all, before we discuss diversity, I want to highlight the main way people evaluate diversity, compute diversity in ML and in the sciences in general. People typically use average similarity as a measure of diversity. So you have a similarity function, you are given a collection, you compute the pairwise similarity between the items in your collection, and you just average those pairwise similarities as a way of measuring the diversity of the collection. I'll show through 4 examples why that is a bad way to evaluate diversity. Take this a controlled experiment, this controlled setting where we are given the collection in this case is 3 different shapes, and we have 2 of them. This metric called internal diversity is just basically average similarity. It's also called internal diversity, int-div. Here we know that there are 3 distinct elements. The score outputs 0.78. Average similarity is 0.67. In the same setting, where we now look at, instead of looking at shape, we look at color. So the similarity function is that if 2 items have the same color, give it similarity 1, otherwise give it similarity 0. So yellow is 1 and black is 0. Here it was, if 2 elements have the same shape, give it 1. If they don't have the same shape, give the similarity 0. That's when you got here. So here they have the same diversity. So average similarity is outputting the same number, which is great. But when you compose those 2 notions of similarity, so looking at both shape and color, meaning if 2 elements, you're using a similarity function that says if 2 items have the same color and the same shape, then assign them a similarity 1. If they either have the same shape or the same color, then assign them a similarity of 0.5. If they have neither the same shape nor the same color, then assign them a similarity of 0. Then you have this profile that brings more diversity to the collection we're given, and this score, average similarity, isn't able to detect that. It's still saying that it's the same diversity as this one and this one, which is wrong. Another failure mode for average similarity is that when you give it when you have a mixture of Gaussians, so just groups, consider them as K groups, a mixture of K Gaussians, K groups, and for each component, each group is called a component. Let's say you increase the variance between each group increasingly, going from left to right. You see that we are here increasing. Here we have 5 components. We are increasing the variance for each component when we go from left to right. The internal diversity doesn't change. So average similarity doesn't detect that we are actually introducing more diversity to the collection. That's another problem. A third problem is that when you use average similarity to score different molecular generative models, so remember you want the molecular generative model to be able to output diverse set of molecules. So we want to be able to evaluate diversity for molecular generative models in a good way. Average similarity cannot do that. It can give you a bad ranking for diversity for generative models. So here I'm showing 3 heat maps. Each heat map, yellow is basically, whenever you see yellow, it's like similarity is 1. So it's duplicate. Areas that are yellow means they are duplicates in that. And black is that there's no similarity. And so looking at these 3 boxes, we can see that this is the real data. This is the heat map for the real data. This is a molecular generative model. This is another molecular generative model. The HMM and the AAE are 2 different molecular generative models, and real here corresponds to the real data. You can see that the AAE is the most diverse one, just looking at it visually. Then the next most diverse one is the real data, and the third least diverse one is the HMM. Average similarity is scoring the HMM as actually the most diverse one. It's giving it a high score, which is completely false. So it can give bad ranking to molecular generative models, which is bad. A last example is when you introduce duplicates. So here we're looking at a setting where we were testing it on CIFAR10. So we use CIFAR10, that's an image data set. you look at CIFAR-10 and you 100, just pick 100 random samples of CIFAR-10, then duplicate the most rare items in that sample of 100 images. Pick the most rare one, the one that looks the oddest, and then duplicate that progressively. And as you duplicate, make sure the size of the collection remains the same. So you are getting rid of some of the other images. Normally that says that the diversity should be decreasing, right? So here, this heat map is the original heat map for similarity kernel for the 100 random 100 images. Then this is the heat map when we introduce more of the most rare image in the sample. This is even introducing more duplicates. You can see that the average similarity starts by increasing instead of decreasing from the get-go. It starts by increasing because you are introducing the one that's most rare. So it's acting like you are introducing things that are more dissimilar to what was there before. So it first starts by increasing before it then decreases, because at some point you have introduced enough of that rare item, that rare image, that it starts to see that you are actually just using the same thing. For this thing called the Vendi score that I'll discuss some later, discuss soon, is it doesn't have that problem. It decreases from the get-go. It can notice that you are duplicating. So let me get into Vendi scoring. Vendi scoring is basically trying to come up with a set of tools that can allow to evaluate and enforce diversity. The way we got to it was looking at actually what do we want out of a diversity metric. So we looked at ecology, which has a bunch of axioms for what a diversity metric should satisfy. One axiom being that a diversity metric should be an effective number. So if you give it a collection of n, and all the n items are distinct, the diversity metric should output a score of n, and if they're all the same, it should output a score of 1. Partitioning is another axiom, meaning that if you have a collection and you partition it such that no subset overlaps and all elements in two different subsets are very dissimilar, are completely dissimilar, then the diversity of the overall collection should be the sum of the diversity of the subsets. If you duplicate an existing element in a collection by letting the collection grow, meaning that you don't delete anything, then your diversity should not change because you're duplicating an item. If you permute two elements of the collection, diversity shouldn't change. That one is trivial. And monotonicity is that if I use two kernels, the second one introducing more similarity between the items, then the diversity should decrease. Another desiderata we want, because if we want to apply these diversity metrics to a diversity metric to ML, we want it to be reference free. We just want to be able to take a collection of items and assign it a diversity score. We don't want to have to fit a probability distribution or use the training set to compute the metric or anything like that. So another insight we got out of ecology for building a diversity metric is that diversity should be exponential of an entropy. And I refer the reader, the one watching this, to refer to the paper, the Vendi score paper in 2020 for why this is a good thing to do. So once we know that diversity should be defined as exponential of entropy, one naive way you can go about it is just take your collection x1, xn, fit a probability distribution to it, p theta x, and then compute the Shannon entropy, the exponential of the Shannon entropy of that distribution. This is not good because you will have to fit a good probability distribution first. And second, even if you fit that probability distribution, it needs to be tractable, which is almost never the case for interesting distributions. And so this will be, we will have to find a way to approximate this, and we don't want that. So we looked at another form of entropy, which is the von Neumann entropy in quantum mechanics. It's defined as, there's a negative sign missing here, negative trace of K log K, where K is called the density matrix of the quantum system under study. So we think that this is a flexible form of entropy, and this is what we use to define the Venn score. We just had to figure out who K needs to be. And to figure out who K needs to be, instead of density matrix, we use similarity matrix, because in our axioms for diversity, we kept mentioning dissimilarity and similarity. So you have to be able to define similarity between items. And so we thought about using the similarity matrix in the von Neumann entropy to define the Venn score. So we define the Venn score of a collection x1, xn under a given kernel function k as the exponential of the von Neumann entropy of the normalized similarity matrix. You normalize in order to get good interpretation so that everything fits well, basically. And this is also the exponential of the Shannon entropy of the eigenvalues of the normalized similarity matrix. So it looks at how spread the eigenvalues are. And the more spread it is, the more diversity you have. You can go beyond von Neumann entropy and use Renyi entropy, which is a generalization of von Neumann entropy. Renyi entropy introduces a parameter Q, and you can define the Vendy score. We call these the cousins of the Vendy score because you now have an entire family of metrics. You can define a family of metrics indexed by Q as exponential of Renyi entropy of the eigenvalues of the normalized similarity matrix, where similarity is given as an input. Here, the lambda are the eigenvalues of the normalized similarity matrix, and K is the similarity function. The parameter Q controls how you assign sensitivity, whether you are more sensitive to the common items in your collection or the rare items in your collection, or whether you put sensitivity equally to each of them. If Q equals 0, all species are given the same weight, and the diversity reports the total number of items, regardless of whether they're similar or not. So that's a bad, you don't want to use Q equals 0. It's not informative. You want to use a Q that is different from 0. When Q equals 1, you recover the original Vendi score, the von Neumann entropy, exponential von Neumann entropy. When Q is infinity, all the weight is assigned to the common species, and the metric becomes very sensitive only to common species. So that can allow you to see duplicates and everything. When Q is not 0, not 1, not infinity, and is less than 1, then the metric becomes more sensitive to rare items, and you can use that to do outlier detection. So we basically have defined now here the expression you're seeing, a family of metrics that can allow us to do a lot of things, including evaluating generative models. We want them to be good. Remember, we wanted them to have no collapse, to be diverse, to not memorize, and to not duplicate. This expression, this family of metric, we have used it to do all of that, to evaluate generative models on all those aspects, but also to enforce diversity such that you have sampling algorithms that cover the space in a diverse way, making sampling better, so molecular simulations, making them better, and making search algorithms for materials and molecules better in the sense that you can get to the desired material in a more efficient way. And I'll show results on that now. Let me show results on that. So the first results is in using the Vendi score, so diversity as a way to make search better for discovery. Remember, search was one way to get candidates to test in the lab. So you want to actually make sure that the ones you find are very likely to be successful when synthesized in the lab. So what we've done is use the Vendi score to incorporate it into Bayesian optimization, which is the typical way people use the thing that I discussed at the beginning. We just incorporated the Venn score as a way to filter the database that you have. So you have a database, a small database of labeled materials. Here, the materials I'm considering are metal organic frameworks. But there are more data that are unlabeled that we have available, and we want to make sure that we find a desired material from this pool of unlabeled materials. And the Venn score can help make this loop find that desired material more quickly. We found, for example, this metal organic framework. It has a node and a linker like all metal organic frameworks do. And it's the one that's beating right now the state-of-the-art MOF for ammonia adsorption. It's at 30 ammonia molecules per kilogram of framework, whereas the current best one in the market that's being sold in the market in industry is at 20 to 25. So we found this better one using diversity in the loop of Bayesian optimization. Another way diversity can help is in improving molecular simulations. So molecular simulations is something all scientists do. It's a sampling problem, basically, one of the techniques I mentioned, but it's used beyond just sampling. It's also used to study, actually understand these materials and molecules, how they behave and everything. And it allows us to, estimate physical quantities of interest that are hard to do experimentally. So people resort to these molecular simulations a lot. What happens during molecular simulations is, you have for example, a molecule that has different conformations. For example, this one, depending on how it is, it adopts different configurations, and you want to be able to find both of those. You want to study the phenomena of how it goes from one to the other. So you need to be able to observe both of the transition from one state to the other. But that transition involves a very large energy barrier, and is in molecular simulation, typically get stuck in one configuration for a very long time. So we have used the Vendy score to make that sampling algorithm faster, so that they can explore the space and jump from one configuration to the other in a very fast way. That's what I'm showing here. The Vendy sampling is the molecular simulation algorithm that uses the Vendy score. Replica sampling is a baseline molecular simulation algorithm. And you can see that Vendy sampling quickly, crosses energy barriers and is able to cover the full space. So that's another benefit of diversity for AI for science. We have also used the Vendi score to be able to evaluate generative models. We wanted them to not collapse. We wanted them to not memorize data. We wanted them to not duplicate data. And so in our recent paper, the Cousins of the Vendi score, we have used the Vendi score to detect memorization. And I suggest the viewer to consult the paper for more details, given I'm running out of time. Yep, I'll close with two takeaway messages. The one takeaway message I would want for you to get from this is that the future of the scientist's work will heavily involve AI, but we have a few roadblocks to tackle before AI can effectively enable scientific discovery. We need better evaluation. You cannot make something better if you cannot evaluate it. We need better data curation and benchmarking so that people can test methods on open data, and also for very large databases that we are able to actually have methods that can select a subset of that data in order to build data efficient methods. We also want better methods in general, better generative models, better sampling algorithms, better search techniques. The second takeaway is that the Vendy scoring, which is what I've introduced here briefly today, brings a new set of tools to science and ML, allowing us to evaluate datasets and models and criteria such as diversity, and also enabling detection of duplication, memorization, and outliers. And Vendy scoring can also enforce diversity for better sampling. So Vendy sampling is an example, better search, Vendy Bayesian optimization is an example, and better generative modeling. This is what I have so far. I'll thank my student Ame Pasarka at Princeton, and Dan Friedman, who's another grad student at Princeton, with whom I've worked on these things with. And I also thank organizations who are funding our work. For references to know more about some of the things I've touched on today, I would refer you to these three papers. Thank you.
Thank you very much, Prof. Adji, for this very rich presentation. It actually made me reflect on my own research, where I was actually, I've used some diversity measures before, and I'm questioning a bit everything. And yeah, you've also touched upon some challenges that some research communities face. And I wanted to ask you about the data sets and benchmarks, because I mean, I was more in the communication field, and in the wireless communication field, most data sets are proprietary. So like the vendors don't want to share it, and so that's kind of hindering the progress for the community in that area. And I was wondering, for your area of expertise, what is stopping people from creating these benchmarks and releasing these data sets? Is it also the same worries, or?
I think it is that. I think there's a lot of currency in having, made something in the lab, gathering a lot of data sets. You can do a lot of works, publish a lot of papers based only on that data set. So people selfishly prefer to keep that to themselves, unfortunately. But I think the data problem also comes from the fact that sometimes even getting a lot of data is impossible, because the whole loop can take, entire prohibitively long time. So you cannot realistically actually collect any reasonably sized data because of the nature of the problem itself. So we also do need to think about other types of ways of tackling these discovery methods. So sampling is one good good approach to that, meaning that you don't actually need data. You need to be able to deal with a function that that is known to be the true probability distribution.
I mean, that could also help, for example, in reinforcement learning that is done kind of offline to explore better.
Yes.
I know that there's a lot of intersection between the two areas, and
Yes.
like drug discovery, material discovery
Yes.
has a lot of things, and this could be generalized to a lot of other applications. Another thing that you've mentioned, like before just talking about the Vendy's, the diversity and stuff, is the issue of measurements. I also feel that it's an issue for many areas. Like we just keep running towards like publishing or making, but there is no first of all, like work on measurements is not that encouraged, and secondly, there isn't a unified way to measure things. Like maybe people just adopted accuracy as the only metric, and then like job done. And so what do you think should be done to actually change this way of thinking? And
I totally agree with you that there's so much needed to be done in terms of metrics, benchmarking, and evaluation. And there's in ML now we're waking up to that. So people are starting to work heavily on those benchmarking and metrics and things like that. There's a whole metrological AI that's about metrics that's coming up right now. But in AI for science, we don't have that because it's a relatively new area. We don't have that, and that's needed. I think the only way to incentivize people to work on it is to show that it's actually these metrics can actually allow you to do things you couldn't do before. And that's what we're trying to do with the Vendi score set of metrics to show that they can be actually you do need them in order to discover things, which is what we showed with the meta-organic framework discovery, that you actually can beat the market, what's in the market, by incorporating this metric into your search pipeline.
I see.
Yeah.
That's
So
actually
I think
a great
that's the
idea.
one thing. Yeah, one thing that can convince people is to show them, oh, you can get better if you do it.
That's actually a good selling point.
Yeah.
Another question from optimizers.
I know it's more costly because you know to go and find those cases.
So the question is more about well, first of all, can you please stop sharing the screen so we can actually see you better? Sorry.
Oh, can you see now? This is,
Yes, thank you. So, in your opinion, what does Africa in general and maybe Morocco need to catch on these the developments in different areas using AI? I think we have the talent, but I'm not sure. Like the talent is getting scattered everywhere, and how can we help actually our countries with the race towards AI?
Yes, I think it will involve a collaboration of private sector and the public sector, and especially the government needs to put priority. This is for literally, I think, many countries, right? To make sure that the government understands the importance of AI and funds efforts towards democratizing AI, educating people about AI, and training people about AI, and doing research in AI. So more funding, I guess, never hurts. Scholarships for students, research funding for researchers so that they can, publish. Because when you publish, you actually need to pay for some of these venues. Like Nature would ask you to pay a fee if you want to publish open access, even after your paper is accepted. Or you need to pay. It's dividend
And the fees are...
Not everyone can pay it. Yeah, so funding is definitely needed. And yep, this is a high fee. And so, yeah, I think funding is very critical, and also putting platforms online that that the youth can access to directly interact with the material in their own language is, I think, something that's also very needed.
Yeah, and maybe like some government funded compute to enable research labs to be also competitive. I mean, there's a race towards scale, and that's creating issues.
Yeah, and the infrastructure.
And what can we as a community do? Like, I mean, we are trying, but do you have any other ideas that we can do to help?
I think
what kind of initiatives, for example?
Sorry. I think you guys are doing amazing. They're having a lot of activities, this conference being one of them. I think is a great, you are doing amazing. In the landscape of AI in Africa, I would say that MoroccoAI is doing amazing in terms of cultivating an AI culture in Morocco, in the ground. I think you're doing, actually, we need to learn from you what you all are doing and encouraging that. I think you're doing amazing. Everything when it comes to, just publishing news, what's going on in AI, what are the opportunities, being present and organizing these gatherings, workshops, going people to talk about AI, all of that, summer schools, all of that you are doing, and all of those things are needed and are great ideas. Yeah.
Thank you very much. Do you have any last words for the attendees and the MoroccoAI community? And maybe you can speak also in French.
Yeah. One final word would be that I think AI is already transforming our society in major ways, and that I encourage anyone in any field really to learn about AI and see how they can incorporate AI in their work. And that even though there's many fear around what jobs will be lost because of the technology, there will be many new types of jobs that will be created because of the technology, and that I think we should embrace AI while being aware of the downfalls that AI can bring so that we can mitigate them. En français, ça va être difficile parce que je commence à perdre mon français, mais je disais que j'encourage les jeunes et tout le monde dans, dans tous les domaines d'utiliser l'IA, de s'informer sur ce qui se passe dans le domaine de l'IA et d'essayer d'incorporer les avancées de l'IA dans leur travail, dans ce qu'ils font, parce que ça peut, même s'il y a même si l'IA peut poser des problèmes, spécialement en ce qui concerne comment on dit, unemployment, oh mon Dieu. En ce qui concerne l'emploi, oui, en ce qui concerne l'emploi, je pense que l'IA va transformer notre société et qu'il faut plutôt voir comment l'adapter, comment l'utiliser de jour en jour, plutôt que d'avoir peur de l'IA. Bien sûr qu'on doit être conscient des problèmes que l'IA apporte, que nous n'avions pas avant, mais je pense que l'IA nous apporte beaucoup plus et qu'on doit essayer de l'utiliser au mieux en étant conscient des problèmes. Merci.
Merci beaucoup pour votre mot et c'est très encourageant. Je remercie tout le monde qui sont toujours avec nous. Je pense que c'est notre dernière session. Donc, merci encore, Prof. Adji, pour avoir terminé cette conférence en toute beauté. Oui, c'est ça.
Merci beaucoup. Merci de m'avoir invité.
C'est un plaisir.
Bye.
Bye.